that my work has relevance so far. And yeah, hello everyone here, and also good morning, good evening, or good night around the world. Yeah, I'm talking again about some topic of understanding reservoir computers. It's an awfully long title. A short version of it could be just consistency capacity. And yeah, it's mostly about a paper that we just recently submitted and is currently under review. And yeah, I'm going to spend, let's say, the first 10 slides repeating a little bit or summarizing all the relevant context of consistency in reservoir computing before I actually come to the new stuff that we have written down in that paper. So it's all about understanding reservoir computers in contrast to the application of reservoir computers to, let's say, data modeling. Yeah, the reservoir computer is a large dynamical system like this, driven by some input U of t. You could have a continuous time version of it or a discrete time version. Doesn't make much of a difference. It just depends on what you have available. And the reservoir acts like a hidden layer that creates a high dimensional embedding of the input data. And from this embedding, you facilitate actually the readout, the construction of a target output, which is here this y of t. So you want to approximate some target signal z of t, and the actual signal that you read out is y of t. Typically, linear regression or ridge regression is applied to minimize the mean square error between the readout and the target. And well, that's, let's say, in a very nutshell, what so there's the minimal ingredients of what reservoir computing is, and this here could be a numerical dynamical system, but reservoir computing is particularly interesting because these can be physical systems where you actually don't really know or don't have control over anything that's going on here, and you not necessarily need to have a model of this physical system that you employ for computation. So, and our goal is to understand the relationship between the dynamics, looking at it as a dynamical system, and the function in terms of the performance that it has when implementing a particular task. Now, let's think a little bit about this. So to say, why the endeavor of understanding reservoir computing like this. From a data modeling perspective, you might say, okay, reservoir computing is one out of many methods. You look it up, you plug it in, tweak a little bit here and there, optimize some hyperparameters, try to maximize the performance, and then evaluate how good it does. Maybe you're creative and combine a little bit the method with different methods, make some changes here and there, just in order to get the best out of your data application that you want to have, and that's it. Don't need to understand very much. You need perhaps some intuition of what you get by experimenting with it. Then you might say, okay, that's not good enough. Let's have a closer look at this works to identify what are the key parameters, because that system has lots of parameters, lots of design principles. Some of them, there's more of a consensus in the community. Some of them is up to the individual team that works on the topic. So you might study it in order to just make a bigger improvement in your data application. No? Does it make sense? So you want to squeeze out perhaps a few more % of performance by learning about the reservoir computer. But even that, which might justify, let's say, doing an honor project or two, or maybe even a PhD thesis, is not really hitting the core so it's not really hitting the point of the reason why you study reservoir computer like this. So I guess most of researchers in the community are more or less consciously aware of that particular reservoir computing has a prominent role, has a key role in the larger discipline of understanding, of studying intelligence, be it artificial intelligence or natural intelligence. That means whatever you learn in there has usually broad impact in adjacent disciplines like neuroscience or machine learning, for example. Yeah. So it's just generally interesting just trying to understand all this very complicated machinery. And yeah, I believe there's a lot yet to be understood and a lot of potential also. We're definitely not the only ones doing this. There are other teams, other approaches. Our focus here is we're looking at the echo state property. That means ideally your reservoir state is a function of the input state only. It doesn't add individual dynamics on top of it. And that's also related to the fading memory property. You can think of, for instance, this map here. If you just replace this x of t minus 1 by the expression here, and then you get some nested expression, so to say you get a recursion. So to say you're unwrapping the recurrence of the reservoir and get this dependence here. And fading memory is just about, is this going to converge as we go to minus infinity, or is this not converging? So to say, do we have some dependence on the initial conditions left? So that's the points where we are looking at. That brings us down to dynamical systems. So I probably have presented these slides a couple of times before, but they're they're essential in this context. Now, all goes down to the basic drive response scheme. So they have some source u of t, and then there's a dynamical system responding to that source. And they can be in a state of general asynchronization or not, depending on properties, let's say, of what comes in and parameters of that system. So GS would be functional relationship between drive U and response X. This negative conditional Lyapunov exponent indicates a contraction that guarantees stability of that manifold. And the other case, the positive exponent here, leads to some blurred relationship, so actually not a functional dependence, with some level of noise where the exact state depends on the initial condition, or yeah, whichever source of noise. And this can be unwrapped by this replica experiment. You just provide a copy of the system, and when there's a functional relationship between U and X, you expect the same relationship between U and X prime, and you can then measure the same thing by means of a linear relationship. And so whatever nonlinear relationship there was between U and X, this replica experiment maps it to a linear relationship. And because this is so essential, just in order to make it really clear that we're not just measuring a nonlinear relationship using a linear measure, which is something that kind of doesn't make sense. But we're actually using this replica experiment together with a linear measure. So here in the top row, there's some examples of input-output relationships. That could be, so to say, the input of a reservoir and the response of a reservoir coordinate, and various degrees of functional dependence. So that's what it's all about. Could go, so here you see the number that in the end already measures these degrees. This is what we call the consistency correlation. Here is no correlation, that's number 0. You just see something that's completely independent, so also by means of mutual information, you would not be able to detect anything. Yeah, some intermediate degrees, and this here is a complete functional dependence. Why is this interesting? Well, because it's not as simple as these 1D portraits that I have here. In reality, if you take into account the high dimensionality, including the memory dependence, these functionals that we're investigating are extremely complicated. And it could be a situation like this one here, where there is actually a functional relationship, but it's so complicated that you see it already in this point cloud. When you don't have enough samples, you don't have enough resolution, there's no chance to detect this. So here in this work by our colleagues, they presented an example of a relationship of a really well-defined and clearly detectable relationship, detectable by means of the replica experiment, but not by means of any time series analysis. This means correlation or mutual information were perfectly 0. whereas this consistency correlation, so to say this after unwrapping through the replica experiment, indicated this nice and clear dependence. Okay, and consistency is about measuring, not just identifying the complicated dependence when it's there, but measuring the degree of dependence. That means all of these input-output relationships, after unwrapping, when you compare the response state with its replica, give you something that has a symmetry that allows you to apply the linear measure, namely something that's comfortable going hand in hand with a linear correlation coefficient. And this is this gamma square that takes just, if you have enough data points, it's always non-negative, and that's how we measure this dependence. The concept of consistency is a little bit more than that. It's not just about measuring the degree of functional dependence between two dynamical systems, but moving closer towards reservoir computing, we're allowing an arbitrary system. That means that's why I pointed here a black box. So an arbitrary, including physical systems. And also arbitrary drives. That means could be some real world signal or some information carrying signal, encoded a page of Wikipedia in there, somehow injected in your black box. So the concept of consistency is meant to quantify this relationship between input and the state of this black box in a very general setting. No? Yeah, and what's left to say about this? The consistency that you measure by the agreement of this of original and replica output is usually a function of both the parameters of the black box, which is sort of expected, but it's also a function of the driving signal. That was one of the first things that was highlighted here in this pioneering work, namely just by changing the amplitude of the drive from 0 to some finite value, they observed a shift in the level of consistency, just because you were exciting different operating regimes of the dynamical system that was injected. And here's also some experimental example showing just by changing some parameter, you measure different levels of consistency. Okay. Might be boring to consider just, okay, you have a degree of functional dependence, just a scalar measure of your dynamical system. So this is something that is just better than the classification of, okay, is there a function or is there no function? And our recent work, and especially T3 was involved in that, was aiming at making more out of it. No, it's better. First we looked at the multivariate case, because your black box in the very first settings just produced a scalar output signal, and then okay, you apply the correlation coefficient, and that's it. How does the multivariate case work? So that's, yeah, we find a nice solution to that, and also refined the analytics, verified numerically by many different examples and settings. That is a well-defined procedure. This here is just a summary of that procedure. So you start with a normalization step of your time series. That means you record multivariate time series. For instance, all the response variables of a reservoir could be in the order of hundreds or even thousands. This is the X of T. And determine first the covariance matrix. This is by construction positive semi-definite, and we can decompose it like this and calculate then a sphering transformation. So that decomposition and sphering transformation applied to the coordinates, you can think of it here geometrically as this image. So the covariance matrix, the eigendirections, the principal directions of your response are these orthogonal directions here of this outer black ellipse. And when it comes to consistency, now we bring into play a replica system. That's what we need in order to detect consistency. And analog to the correlation for the scalar variable, we look for an agreement of original and replica. And this agreement, so to say, what the common response to the signal is, in the multivariate case, something like an inner ellipsoid that we want to isolate. And we can isolate this by going into the normalized coordinates. So what was the full response is now this unit circle. And now the inner circle has also a well-defined set of orthogonal characteristic directions, and these are the consistency components. And what was previously the consistency correlation, just a number between 0 and 1, is now an entire spectrum that's these gamma k squared, the eigenvalues of this cross-covariance matrix here, which measure for as many degrees of freedom as your system has, a characteristic spectrum of consistency directions. Okay. Here's an example of how they look like. That's something that we also got recently published in a conference paper that Thomas unfortunately wasn't able to attend in person. It would have been the ICANN conference in Bratislava, but nevertheless, they decided to publish the conference proceedings. So here we have, just for 3 different types of reservoir networks, these consistency spectra or consistency profiles for different levels of observational or intrinsic noise. What we always see, they have this generic shape. So to say there are some components, the leading components, which are highly consistent. So these directions in phase space, they carry all of this, most of the signal power. And there are some components at the opposite end of the spectrum, which are highly sensitive to noise, or even if you go beyond the edge of chaos, and they are going to immediately drop down. And of course, depending on the degree of noise and all the details of the network, you're going to see different shapes in particular. Next step is try to connect this with the reservoir performance, because so far it's just, so to say, some generic measure of the of the reservoir. If we have a target, so far we talked about consistency, we didn't do any reservoir computing, but if we now move to reservoir computing and have a target, and we implement the regression and measure the correlation between the target and the actual output of the reservoir, for instance, in terms of a correlation coefficient, we are able to actually express this correlation in terms of the consistency coefficients that we previously calculated. We need to go into the characteristic coordinate system for that. So we need to go into this normalized coordinates and also rotate them into the into the directions of the coordinate axis. Decompose then in a consistent and an inconsistent part of the response. That's also a part of what I spent more time explaining in some of the previous talks. So you can always split the response into something that is a functional response and something that is noise-like. And rewriting it like this, the least squares result of the readout vector in these coordinates looks like this. So we can write it as this consistency coefficient times some correlation coefficient between this the coordinate and the target. And the output also writes then as, so say, this product times the actual component. Plugging this back in, we see that the correlation, the performance, is just a simple expression in which we have something. This is the consistency spectrum, and the AKs are something task dependent. That means the consistency spectrum is task independent, just a measure of the reservoir, how it responds to the input. And these A's, they are, well, like Fourier or Taylor coefficients. So this is something to express the target in the coordinates of the reservoir, and therefore task dependent. The same expression here below the square root recurs in the normalized mean square error. So we said, okay, if we want a generic performance predictor, the best assumption that we can make about these AKs is that they are actually independent of the gammas. So we can split off this sum over the gammas. And this led to the consistency capacity, which is actually the main topic that I want to talk about. Consistency capacity is just the sum over these consistency coefficients. And it turns out, in terms of these previous matrix coordinate transformations that are presented in the algorithm, it's just a trace over this cross-covariance matrix between two replicas. It's very elegant, actually. The trace, so this number, this capacity theta, can take numbers between 0 and n, the size of the reservoir. It's numerically very robust. That means robust against finite size effects. For instance, these spectra, they are very well averaged. So to say, there's been a lot of computational effort behind them to get them as nicely as this year. But typically, you see something like, for shorter samples, you see the spectrum is elevated here in the front part, and it even drops into, so to say, unphysical negative values in the end part. These are finite size effects. But when you sum over the entire spectrum, it turns out the positive and the negative deviations cancel each other very well out, and the resulting capacity is, in the end, very robust. So you get meaningful capacity results even for, let's say, some few thousands of time steps only. No? So it's very robust. And if it's not robust enough, you can introduce even regularization. You can do the same thing like in Tikhonov regularization for the regression step. You can introduce this term lambda times identity in the covariance step before you even calculate the spectrum, which is something equivalent to adding noise. And this gives also a little bit more of meaning to the entire procedure, because you might say, okay, if I set up my reservoir numerically to be fully consistent, all of these gammas are 1, and the capacity is just n, and then so what? But since reservoir computing, okay, that's in the numerical part. In physical systems, of course, all these gammas are something between 0 and 1. No? There it has relevance. But even in the numerical part, you apply usually ridge regression. You have some non-zero regularization term which suppresses effectively all these smaller components. And then this effective capacity, so to say, the regularized consistency capacity, tells you how much of the reservoir is actually left after regularization. How many degrees of freedom are still available in order to compose your target function. So regularization is a part of it. And in the following, so yeah, let's have a look at this. So this is how this capacity measure looks like, with one of the most important parameters, namely the internal gain of the reservoir. That means when rho is equal to 0, the reservoir is disconnected, and rho is a global prefactor of the internal weight matrix. It means as you turn it up, you're increasing the weight of the recurrent feedback until at this point here, this is the edge of chaos, rho c. You enter into a chaotic regime, and then the function breaks down. And this breakdown, as you see, is indicated by the capacity levels. You see how it gradually breaks down, so that it's not an immediate destruction. There's still something left that operates reliably. And yeah, let's have a look at these different regularization levels. It's interesting. So with a very small regularization, you see essentially in the stable regime, you have full capacity. This is a network of 100 nodes. You have, so to say, full capacity in most of the useful regime. But even with that little regularization, here at these very small values of rho, apparently the reservoir is very sensitive. And yeah, the 10 to the minus 4 is, let's say, a typical regularization parameter. You see, so to say, how this regime is the most robust overall, and lambda equals 1 is just, well, kind of the upper end of what you may have. Now, the actual novelty. So we learned that we can look at the reservoir computer as a dynamical system, apply this consistency measure to measure the degree of functional response to the input signal. But that in the same way that we moved from a single output to multivariate output, now we can ask our question, can we perhaps resolve the capacity for multiple input channels? Can we say how much capacity is allocated, for instance, if you have 2 input channels, how much capacity does the reservoir allocate to this input channel and how much to the other? No? And yeah, that's, as you see, this was what was previously apparently very simple, becomes now rather complex and perhaps even useful. Let's see. Now, to disentangle this. In order to measure something like this, in order to measure for multiple channels something like a partial capacity that is assigned to the individual channels, we modify the replica test. So previously the replica test was you drive the reservoir repeatedly with the same input signal in order to examine its response to that repeated input signal. But here, we say, okay, we have 2 input nodes. One of them, we call them the or that one signal, we call it the information signal. It's something that is relevant. This is the one that we focus on in terms of capacity. And the other one, it acts like a perturbation. That means it's not going to be repeated. It's going to be just randomized. Okay, that's the key. So to say, this partial replica experiment, repeating one channel, and the other one is drawn. So to say, independently, new realizations are fed in. And then, yeah, do the same thing again with the reservoir variables because they're going to have also some partial agreement. We can do the same multivariate time series analysis. Question is, do we get something like this, that we have a total capacity, which would get by repeating the entire input, which is the sum of capacities for each of this channel? Let's have a look. So this is the outcome when, so we have introduced a parameter here. The parameter is an input gain parameter that varies the weight between these 2 input channels. That means the information signal S of t comes now with a weight alpha S of t, and the perturbation signal eta of t comes with 1 minus alpha. And this way we can tune the gains between there's just one signal or there's just the other signal. And we just measure this capacity and normalize it by the total capacity that we would get if repeating both of them simultaneously. So depending on the regularization level, we get different outcomes. So this lower curve is the lowest level of regularization, or almost no regularization. This other curve, which is close to the dashed curve, is for very high regularization level. Well, you see, alpha equals 0.5 is the point in which both signals are equally have an equal amplitude. We would expect to have some sort of symmetry there because none of these input channels is distinguished. And the symmetry is in fact given, so this curve actually is symmetric around this inflection point here. And so do also these other until they somehow drop off. So the strong regularization curve can actually be explained by a simple mean field model. The mean field model considers just a single mode responding in the sense of, so to say, yeah, the most powerful principal component or something like this. So some particular direction phase space that carries the most signal power. And the assumption is just that this mean field consists just of alpha S of t plus 1 minus alpha eta of t. That's the entire mean field approximation. And when we then calculate what is in this mean field the power with regard to S of t, well, this is alpha squared here in the denominator, in the numerator. And the total power is just because S and eta are uncorrelated signals, alpha squared plus 1 minus alpha squared. And this gives exactly this dashed line here. So the mean field of so this most powerful mode responds as if you just add up the two signals. But the reservoir has obviously more degrees of freedom than just this single component. And they come into play when we turn down the regularization. So that means something happens here, we break the symmetry, and the two capacities, so if this is the capacity related to the information signal, we expect the same value for the other signal. They don't add up to the total capacity. There's something is missing. Yeah, so the fact that we're below 1/2 here means that some capacity is missing in this formula here. And this leads to the idea of multiplicative terms. That means there is some capacity that, so we have identified some capacity exclusively allocated to one channel and one exclusively to the other, but apparently there's also some mixed capacity allocated to both of them. And this simple example here illustrates this. Let's assume we had just this this one-dimensional variable here, consisting of S of t times eta of t, a purely multiplicative term. If we did the replica test with this, the outcome would be that the capacity for S is 0 and also for eta is 0. But still, if you do the joint replica test, you get some non-zero capacity. That means there must be some capacity that we now denote as theta S eta, that is called this then the multiplicative capacity, that makes up for the rest. And here is actually these Venn diagrams, they illustrate the hierarchy of these capacities. For instance, in the case of 3 input channels. So what you first get by doing an individual replica experiment, by repeating, for instance, channel 1 and randomizing the other channels, you get actually just this segment which is exclusively allocated to this channel and analog for the others. And then here's these mixed elements, these multiplicative capacities. If you did the full replica experiment, repeating simultaneously all of the 3 channels, you get the total capacity, which we denote as either theta 1 to 3 or theta 0, which is just a different symbol for the total capacity. Now, what might be interesting to know is these mixed terms here. So these here are of 2nd order dependence and this here is of 3rd order dependence. Is there any way to isolate them? So is there any way that we can do a set of experiments and calculate the individual contributions? In fact, yes, there is. That means if we do now a replica experiment in which we repeat channels 1 and 2, but randomize channel 3, the corresponding capacity for this is this theta 1, 2, that is the theta 1 here in that corner, theta 2 in that corner, plus this 2nd order multiplicative term here in that corner. And we can do the same thing with 2, 3 and 1, 3. Go, so to say, through all the combinatorics. In that case, we have 7 differences. 2 to the 3 minus 1 gives you 7 different replica experiments, 3 for repeating 1 channel, 3 for repeating 2 channels and leaving 1 out, and 1 for repeating all of them simultaneously. This gives you a hierarchical set of these individual capacity measures, which you can then rearrange, which you can then use, disentangle, so to say, and get these, which we denote as the deltas now, these individual contributions. Luckily, the transformation is linear. So the transformation from these raw capacities that we measure directly from the replica experiments and the individual pieces at each level of the hierarchy, which are denoted by the delta, are connected by some linear transformation A. For the example of these 3 replicas, this transformation looks like this. So at the first layer, they are identical. At the third layer, we have, okay, theta 1, 2 is just delta 1 and delta 2, and plus this second order mixed term. Same for the other. And the total capacity, theta 1 to 3, is just the sum of all of them. Now, this gives you some sort of, yeah, lower triangular structure. A simple matrix structure just with ones and zeros. The inverse, here this is an illustration of this inverse. So there's always a very well-defined inverse. For 9 channels, looks quite interesting. I'm pretty sure that people in groups and combinatorics would find that very nice to analyze. For us, it's just, okay, we can solve it, and then that's it, so to say. But you have this interesting block structure of, so here's zeros, and then there's plus ones and minus ones to get your set of deltas from your set of thetas. Now, would be too nice if this just works straightforward. This transformation is getting extremely sensitive as you go to, well, not so high number of input channels. Because reservoir computers may have, let's say, 1, 2, 3 low number of input channels, but sometimes they're going up to the order of 100. And apparently because this entire consistency hierarchy is exponential in the number of input channels, this doesn't allow us to go that far. But even if it's practically possible, so what we see here is, this is M, the number of replica channels. And this is the accumulated capacity. So this is just the sum of all the capacities that you get when doing the replica test of a certain order. That means this is the average capacity of when you repeat just one of the 9 channels. This is the average capacity when you repeat 2 channels simultaneously and go through all combinations and so on. And here, the 9th one is when you repeat them all. And therefore, it's also the highest capacity. You send that through this transformation, and you get then this curve here of deltas, which is also something, okay, it gives you just M times the capacity here at the very beginning, but then it starts to fluctuate a lot, and here in the end converges again. And that's because this transformation has eigenvalues that are like the binomial coefficients M choose K. That means the tiny fluctuations here, if there's a little bit of noise in determining these theta values, even though they're very well averaged, magnifies and gives you this uncertainty at this level. So calculating this is feasible, let's say, until order 5, 6, 7, depending on how much you crunch numbers. Just a little overview, because there are many different quantities involved. So we have these raw capacities that we measure just by distinct combination of repeating input channels. I can average then for a certain order, which is denoted by the omega. Total capacity, that's all what you get directly from the experiment. Then here are the deltas, which are, so to say, calculating the different levels of the hierarchy. And there's also other measures. You can also rearrange them. Once you have the deltas, you can rearrange them and calculate how much capacity is there for each individual channel. And this is going to be this capacity phi for the channel M. So that's what you can get out. Let's have a look at some numerical results. So this is for a different number of input channels. The capacity hierarchy on the right-hand side, it's directly as it comes out of the experiments, so the thetas. On the left-hand side, after the transformation. So these ones here, they are very well averaged, they're robust. Now there's not much noise, it's below the line width here. Yeah, first thing we see is as number of inputs increases, first order capacity drops and seems to saturate. The comparison between the top line and the bottom top row and the bottom row is here at the top, it's a reservoir with 100 nodes and 100 inputs per input channel. And in the bottom row, it's a reservoir with 100 nodes and only 10 input links coming out of each input channel. That means in this bottom configuration, the signals coming out of the input, out of these M input nodes, have less possibility to interfere. And we see this manifest here in a much higher level of, so if you compare the first order capacity here in this setting with this one here, the level of first order capacity is much higher in this configuration, apparently because of the less interference of the signals when injected into the reservoir and less possibility to create mixed dependencies. And yeah, compared with the other configuration, the higher order capacities seem to practically vanish entirely. Also interesting, if you look at the input gain, from very low to very high input gain, first order capacity as expected, when you increase the gain, decreases. Because as you increase the gain, you're operating the reservoir in more in its nonlinear regime. Recall there are typically nonlinear activation functions like tangent hyperbolic or sinusoidal activation functions. And with this high gain, you're operating them in their saturation regime. Whereas at the opposite end, you would expect as kappa, the input gain goes to 0, you're operating just in the linear response regime around the stable fixed point. That means in linear response, you can only have first order capacity because there's no mechanism that generates mixed dependence. Interestingly, this happens, but it seems to happen at very surprisingly low values of this input gain. Apparently, the reservoir is still operating in its nonlinear regime and creating the second order capacity even for very low kappa. The lower picture is a scan of the internal gain. This is the same picture that I had at the very beginning, where there was this transition through the edge of chaos and the breakdown of the total capacity. We see the same profile in the total capacity. So say high capacity until the edge of chaos and then this breakdown. And now we can resolve here for 2 input channels how capacity distributes, and here this is for 4 input channels how capacity distributes among these channels. Another experiment that I found interesting was the modular network. So there's now each of the inputs has assigned a partition of the network, and the modularity parameter controls how much intra partition connectivity there is as compared to inter-partition connectivity. That means with p equals 1, we have a situation of a fully modular network, and p equals 0 is, in the case of 2 inputs, a bipartite network. Whereas, okay, in the case of 4 inputs, it's just, yeah, only reservoir connections among the partitions, but no connections inside. And we see, okay, as expected, in the fully modular case, the first order capacity becomes the the total capacity. Why is this expected? Well, because all of the signal of channel 1 goes to partition 1 and has no chance to mix with the other signal. And therefore, there's no second order capacity. But as soon as we introduce just a tiny amount of links between the 2 modules, immediately the second order capacity is introduced, and also higher orders if we have more than 2 partitions. And last but not least, how much time do I have? 5 minutes left? Okay, then I skip this boring dependence here and go to a more interesting point. Now, so far, we have used this consistency capacity to disentangle, or let's say to analyze the functional dependence on multiple inputs in the reservoir. But we can do the same thing over time. So we can analyze the temporal dependence, for instance, for a single input channel. And before I show the results, I like to emphasize a very basic property of what we're doing here with consistency, namely, it leads to actually a new notion, a new concept of fading memory. So when you ask people in the reservoir computing community, what is the echo state property? Well, echo state property is a strict functional dependence on the input. Okay, and they say this is equivalent to fading memory, because when all memory fades, so to say, when the reservoir doesn't have memory of arbitrarily long time in the past, it needs to converge to this state, namely this strict dependence on the input. Okay. We don't agree with that because, okay, yeah, we worked with consistency. We have a different idea of what this is. But when people think of fading memory, they think of fading memory of initial conditions. And in that sense, it's correct. No? So to say, if all the dependence on initial conditions fades, then this is equivalent to the echo state property. But in an earlier work, we have seen actually, even when we're in a chaotic situation where this is not the case, we can still have some remaining functional dependence. We can still have some response to the input signal. It's an imperfect response, so to say, it's something like when you look through a section of these activations, so that you see some blur. This is exactly what we analyze with consistency. But there's still some remaining impact of the past state of the driving signal. And this impact from the past, even in the presence of chaos, even in the presence of noise, this is exactly what we measure with consistency. Yeah? So we say that fading memory is not fading memory with respect to initial conditions. Fading memory is a fading impact from past inputs. Fading memory is a fading response to past inputs as we go more deeper and deeper into the past. Yeah, and having this tool of consistency, it's easy to quantify this impact. And that's what it's made for. But how do we do that? Now, in the similar creative way that we rearranged, that we redesigned the replica test to account for the individual input channels, we can redesign a replica test to account for individual points in time. So now in the top part, you see an input signal, just a scalar input sequence, and the corresponding reservoir response. And in the bottom part, it's the corresponding replica. So it's the same reservoir, but repeatedly driven with some, well, not the same signal, but a different signal. So if we wanted to do the full replica test, we would need to repeat exactly in the replica experiment that input time series. In order to analyze, however, the impact from a particular point in time, we now shuffle or randomize our input signal, but repeat only one distinct position in time. That means we create something like a surrogate time series that has, so the U of t is the original time series, U prime of t is the replica input time series. That has nothing in common with the original except this one point in time. So this is this highlighted in red here point, which shares exactly the same value. So it's somewhat the inverse of adding a perturbation to the reservoir, and that's actually the idea of probing the reservoir. Now you're adding some a form of a perturbation. In this case, actually, it's a perturbation on all states except one. Now, in this way, we are, so to say, doing a replica experiment for just this single instance in time. Yeah, and that means this single, so to say, synchronization pulse, if you want, or yeah, replica pulse induces some matching between the reservoir states, indicated also here by these red highlighted activations, which then, as time goes by, fades away. Now, because again, the two replica, the two reservoirs receive randomized signals and cannot be related by any means. So all we need to do is, so to say, we have this one instance and we analyze how its impact fades over time as we move forward. Now by comparing the two corresponding reservoir states after some time lag. And yeah, the nice thing is this is essentially equivalent to an M channel replica experiment. So you just have now M channels in time. You can even do the same combinatorics. You can, instead of repeating one point in time in the time series, you can repeat multiple points within a certain time window and do all the combinatorics. Won't go through all this because we don't have time. Actually, you can define some capacity that measures just the impact of this particular point in time. So this, and we define this phi as a function of the time tau as the memory profile, and it has the interesting property, if you allow your window for the experiments to be large enough, it adds up to the total capacity. And this looks like that. We see here these memory profiles. Actually, let's have a look just at this middle dependencies. First of all, we see something fading. That's good. 3 different operating conditions. The first one here, that's for a low internal gain, where the reservoir is supposed to have very little memory because the weights on the recurrent connections are very low. And in fact, so to say, we have a memory that decays very fast after 5 time steps. There's no response anymore to that point. This here is very close to the edge of chaos. We see some dependence that stretches over 20 points in time, and this is here. And this here is memory in the chaotic regime. Still memory fades over, let's say, 20, 30 points in time. It's just that the values are relatively low, and they add up to this reduced capacity as it is in the chaotic regime. Remarkable finding is, for instance, this peak here, which has to do with, well, let's say it's surprising in the sense that you would expect memory to just exponentially fade away. But in fact, it seems to have stronger memory of what happened 3 time steps before than what is being injected right now into the reservoir. That has to do with, let's say, a mismatch between the direction and phase space in which the signal is injected and the leading Lyapunov mode, so the leading Lyapunov vector, which dominates this decay. So if you measured this decay here after this peak, it's exponential. And that corresponds to actually decay with the leading conditional Lyapunov exponent. But this, so to say, perturbation that the input signal creates continuously is not aligned with this Lyapunov vector, and therefore it needs a couple of time steps for the perturbation to rearrange and to align with the most unstable decay mode. That's at least how we would explain this peak here, which is something that you wouldn't see with any other means. And now I'm really running out of time, and therefore summarize. So we have this consistency capacity, which is a measure for the degree of functional dependence of the reservoir on its inputs. If you have multiple channels, you can do combinations of replica experiments and determine a capacity hierarchy, including mixed components across the channels. You can design particular replica experiments over time with tailored time series and obtain a memory profile for each individual channel. If you have multiple channels, you can even make a combination of both. And well, what can you do with this? Perhaps, and it's very likely that this capacity that you measure has some benefits for reservoir optimization, or if you want to predict the performance of it before even doing a task, tailoring a reservoir for a particular task, this might be very helpful. And by construction, it's something that is not restricted to numerics, but it's a form of experimentation plus time series analysis. That means everybody, even including working with physical reservoirs in experiment, can do these sorts of experiments and measure the outcome. Okay, that's it. Thanks a lot.
So, do you have any questions, either online or in person? I'll just ask one, even though I'm technically co-author, I'll ask one anyway. When you have just synchronization of one time point, if you were to do that periodically with some period, would that give you a test of effective requirements and sampling to provide a model of a particular system?
So you're thinking of applying that replica point here?
Yes, so you've got a replica point, one replica point, you've got long time series. And
actually, I mean,
time steps
the way I implemented this is via multiple points, but you always need to check that you exceed the fading memory. Otherwise, I mean, if you enter here in that window, you would see some recurrence here when the next point happens.
Yeah.
But this doesn't answer your question, I guess.
No.
You do this to try and test the memory of the system.
Yes, exactly.
So how do you distinguish between memory and base in the chaotic process?
Just, by the way, repeat the questions so that anyone online can hear you.
Okay, they can't hear you.
No, just for him to repeat the question. So online.
Michael's question was about periodic repetitions of...
Slide, you had 3 plots and one's in the chaotic regime by the bottom right.
Yes, exactly. So Michael's question is about...
And what's caused by chaos.
You
How
can't
do you distinguish the two?
You
so
can't
on the top
distinguish.
One, that's all memory because there's no chaotic behavior, right?
Yes.
But the bottom right, how do you distinguish between what's a memory effect and what's an effect of the chaotic nature of the system?
The question is, how do you distinguish what's an effect of the memory and what's an effect of the chaotic nature of the system? Well, I mean, if you sum these memory curves up, here you get just the reduced capacity, this measure of 40, let's say, out of 100 degrees of freedom. In the others, you see you get something close to 100. There you see, let's say, there you see the effect of, let's say you see how much of the capacity has been taken away by chaos. Although, other than that, I wouldn't know how to well, I mean, what you measure here is.
Could you tell me could you say which is stronger, memory effect or chaotic effect? In that bottom right diagram, could you definitively say which effect is stronger?
So the question is, which effect is stronger? Could you tell? Well, the simple answer would be, okay, if you wanted to make that decision and you set the threshold at 50, in that case here, the chaotic effect takes away more capacity. The way to think about this is the external modulation, the input to your dynamical system, even though it's on a chaotic attractor, modulates this chaotic attractor. So the probability distribution, so irrespective of your initial condition, you have a density that fluctuates with time. And what consistency measures effectively is the first moment of this density function, how it actually responds. In that sense, yeah, I think looking at these numbers and saying, okay, if it's below 50%, and then indeed more than 50% of the variance of your chaotic system is produced by the chaotic dependence, whereas the other part is produced by the dependence on the input.
Thank you.
Yep.
Okay, we have a question from Dimitri in Saloniki. Let me just turn the volume up. We can hear you, Dimitri.
Okay, thanks. Thanks for the nice talk, Thomas, and thanks for being able to attend as well. I have a general
Certainly.
question because from the very beginning, you posted the problem for this reservoir computing that you have a dynamical system that is only the state at time t depends only on the state at time t minus 1. At least that was very clear for the discrete representation of the system. Yes, yes. So what if you have another more complex structure of the system that it would depend on two lags, on the state, the two lags in the past? Because this is this is a kind of a simple scenario for a dynamical system that you have dependency only on the previous lag. You may have more than one. Lags to the past.
Not a problem for this sort of analysis, because this consistency analysis is completely agnostic about the mechanism causing the memory. So whether it's one lag or two lags, or even in the continuous time case, if you have an explicit time delay here inside, it will give you probably some non-monotonic memory dependence, some recurrences, but yeah, it's going to work perfectly fine. Now you're going to see probably an extension of that memory. You can quantify it by that. Of course, there's also the standard memory measures like the linear memory capacity that has been there for 20 years. Not sure, we haven't had a look yet, so to say, what different things our memory profile can tell you than the conventional memory profiles by the standard task. But yeah, you can use it as a diagnostic tool in order to investigate the effects of such.
To postulate this question in another way, what about if you would consider these x quantities as a vector, x and xt minus 1 as a vector? Would this be possible? You talked about the multi-channel, but multi-channel may be different quantities, I guess. Could you postulate the same problem in the vector form?
So here this x is, I mean, the notation, I haven't used the bold notation or anything. It's supposed to be the state space vector, yes. But is this what you're referring to? Or
yeah, yes. But this is scalar. Yeah? As far as I understood, this is scalar, the x. My question is, could it be vector as well? So this f function is a vector field, actually. Because it's common if you have a dependence on more than one lag.
Your vector valued state x to the next time step.
It is common to in the time series analysis. It is common to move from the situation where we have dependence on more than one lags to the state space where you can build up the x as a vector and still have the dependence only on one lag. So the question is whether it is possible to address the problem in the same way if x is in a vector form, not in the scalar form.
I guess one way of thinking about it, Thomas, is that your dynamics on your node is just a function of the previous state.
Yes.
And it could be a more general function of longer lags as well.
Certainly.
I think that's what you're asking.
Yeah, Michael said your f is just a function, so the function is just a function of the previous time step, but what you're asking is that it also could be a function of more than just the previous time step.
And this would be equivalent of bringing this equation in a vector form by using only one lag.
Yes, yes.
In that case, the f, of course, it has to be a vector field.
Yes.
So let's say if it was like dependence on 3 lags, t minus 1, t minus 2, t minus 3, then you could write this same form, but then x would be a vector of 3 components. This is possible to do this.
Yes, yes, certainly, certainly.
Yes. So it's equivalent whether you can use the vector form of this equation here that you have. The x, whether x can be a vector instead of a scalar.
I think the
Yeah, I fully agree. Let's say for the consistency analysis, it's going to be completely okay.
But then your gamma,
as long as you can as long as you can do the replica experiment, and as long as you can record multivariate time series corresponding to these, it's all perfectly fine. What happens in between is actually not critical.
but your gamma square index of consistency, it is defined as a correlation, a square correlation index.
Yes. Mm-hmm.
So in that case, it wouldn't be a scalar anymore, eh? Unless you take like something like the trace of the covariance matrix, or the correlation. So you do something else. I mean, it's not a scalar anymore.
Oh yes, that's true. That's what it's all about. If you have,
you had this slide, just the one before this. You had this definition for the gamma square in the slide before this one.
Exactly. That's.
Yeah.
So here in this case, this example, that is still a scalar.
Yes.
I should have probably distinguished here my variables. So these ones here are now multivariate time series.
Ah, okay.
And yes, and multivariate time series, they lead to this spectrum.
Okay, so you address actually this problem here. I didn't notice. Okay, thanks.
Mm-hmm. Okay, yeah.
Thank you.
questions online or in the room? Or upload? Okay, if there's no more questions, thank you once again, Thomas, and I think it's officially hub time.
Thanks. Thanks very much for attending.
Thank you everyone for joining.